All right, so this is part 4. We're off the ionics and on to covalent. By the way, covalent is only one video. Covalent's very simple. Ionic has all these different varieties. Covalent is simply covalent. So this is going to be a quick video. All you really need to memorize for this is your Greek prefixes, which once you go through it a couple times, it's nice and simple. So covalent molecules. This term molecule really should be applied only to things that are bonded covalently. So for example, water and carbon dioxide, those are molecules. Something like salt, NaCl, is not technically a molecule because it's not a separate entity. With something like salt, it's like Na bonded to Cl, bonded to Na, bonded to Cl, bonded to Na, and so on. First question, how do I know when something is a covalently bonded molecule? Well, the answer is this. You look at the type of element that's involved. Nonmetal plus nonmetal, covalent. So CO2 or C6H12O6 or H2O. Remember from back before, metal plus nonmetal, that's the classic formula for ionic. So NaCl, MgF2, or even when the nonmetal is polyatomic. But notice, or this should say, if any polyatomic ion is present, it's ionic. The reason I had to write this is something like, for example, NH4C2H3O2. It looked like I just wrote a random blob of letters, but I didn't. And in fact, you should be able to recognize two things in here. If you have your polyatomic ion sheet, you should recognize NH4 is ammonium, C2H3O2 is acetate. Anytime you have one or more of these polyatomic ions present, it's going to be ionic. Even though there's not a single metal here, N, H, C, and O are all nonmetals, so you might think that's going to be covalent, but in this case it's not. So it's important that even if you don't have to memorize these, you should still be familiar enough to recognize them when you see them like this. Because if you didn't, you might call this something like nitrogen tetrahydride dicarbon trihydride dioxide, which would be totally wrong. So let's move on here. This, by the way, type 1 ammonium acetate. And if you ever have this, don't combine the H's. It has to be 4 here and 3 here. So ammonium acetate. Note, metalloids can participate in these types of compounds too. So metalloid plus nonmetal will be covalently bonded. Just a quick refresher on where these types of elements are located. On your periodic table, the bold zigzag line, the staircase we sometimes say, that marks where the nonmetals are. That marks where the metalloids are. The nonmetals are to the right, so these up here. So it's carbon, phosphorus, selenium, iodine, and kind of zigzags up all of these. Plus, don't forget our old abandoned friend hydrogen over here. The metals are to the left, with the exception of hydrogen, and the zigzags, that shows where the metalloids are. So in the first 3 videos, most examples were some kind of metal bonded with some kind of nonmetal. That's ionic. Here you have nonmetal bonded to nonmetal. And people often say, well, what if you have metal bonded to metal? Not going to happen. It doesn't work that way because the metals are both positively charged and they're not going to be giving electrons to each other. It doesn't work that way. But in this case, you can have nonmetal bonded to nonmetal, or not metalloid nonmetal. Last thing, hydrogen can be involved too. We kind of left hydrogen out of the ionic compounds. It tends to not be that common. It is possible though. But it tends to bond more covalently. And it'll be referred to as hydride. Just like all these, you're going to change the N to I. Not to be confused with hydroxide, by the way. Hydroxide is OH minus. So for example, if you have NaOH, that's sodium hydroxide. But here when we do covalence, if you have something like PH3, that's going to be phosphorus trihydride. So hydride, hydroxide. Don't mix those up. So, to name your covalent molecules, you need to know Greek prefixes. So you're going to have to memorize these. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. One way to remember tetra, if you ever played Tetris, you'll notice that all the shapes have exactly 4 squares in them. Like whether it's this one, it looks like I'm doing LOLs here, or like my calibration on this board has completely gone crazy. But anyway, if you ever played Tetris, you'll recognize shapes like that. Otherwise, just memorize it. So you have to know what these Greek prefixes are, and we're going to use these to name our compounds. So it's very simple. Let's say we have P3O2. What are we going to call this? Triphosphorus dioxide. So for the first one, you don't say "ide," you say the full name of the element with the prefix. So triphosphorus. For the last one, you change it to "ide," dioxide. What would Ge2Cl4 be? Okay. By the way, disclaimer, most of the examples I make up here, they don't actually exist in real life. They're not stable, they're not possible. It's just a naming exercise. Ge2Cl4. Ge is a it's a metalloid. That's one of our new guys for this, so metalloid. So this would be digermanium tetrachloride. So again, you just stick the prefix in front of each of them. The first one, you state its full name without "ide." The second one, you change the end to "ide." Let's do one more. We'll do S6H8. What would that be? This would be hexasulfur octahydride. So you can go a little slow with it. And the way it spaces out, the prefix sticks directly onto the first word. So it would be, in this case, triphosphorus, and then you do a space, and then the second word, dioxide. So triphosphorus dioxide. This one would be digermanium space tetrachloride. Okay. Now, sometimes, I didn't do anywhere it's only one atom present of a certain element. Now, you guys know this molecule already. CO2, carbon dioxide. Notice what I didn't say. Monocarbon. When the first element has only one, you don't say mono. You just say its name. Okay? But you probably also know this one. You probably have a detector for that in your house. It's carbon monoxide. Notice, for the second one, if it's only one, then you do have to say it. You have to say mono. So carbon dioxide, carbon monoxide. And I'll talk about why I didn't say monooxide in just a bit. So when the second element has one, you have to use mono. When the first element has one, you do not use mono. For example, if we have P3S, this would be triphosphorus monosulfide. If you have PS3, you say phosphorus trisulfide. You don't say monophosphorus. Okay, so once again, use CO and CO2 as your template. You guys know what those are. Use that as your template. Carbon dioxide, carbon monoxide, that helps. Okay. So before we go into examples, just a quick refresher. When do I use mono? You use it when the second element has one. When do I not? When the first element has one. So you never start off a compound with mono, but you have to finish it with mono if the second one only has one. When do I cut out a middle letter? For example, I say mono, but for something like monoxide, it sounds like I'm cutting that out. The answer for when I cut out a middle letter, it's in certain cases when oxygen is a second element. And oxygen is very common. I mean, it's by far the most abundant element on the planet, or even in the planet. Most of the rocks have oxygen as a major part of them. So oxygen, when it's a second part, sometimes you include all the letters, sometimes you don't. Let me explain. So when you have one oxygen, it's monoxide. You don't say monooxide. To say monooxide, the OO, it just doesn't quite work. So this would be like CO is carbon monoxide. If you have two oxygens, you know this, you say dioxide. You don't cut anything out. It's dioxide. You just leave it. If you have three, it's trioxide. Again, you don't cut it out. Why do you cut this out and not this? Because dioxide, sounds fine. Monooxide just doesn't quite roll off the tongue that well. The four oxygens is going to be tetraoxide, but that sounds very clunky when you say it. So you don't say tetraoxide, you say tetroxide. and my calibration is failing me, but it will be tetroxide. So in short, when do you cut out a middle letter? When the element is oxygen at the end, and when it's either an O or an A at the end of the prefix. Now if we look back at our prefixes here, O, A. So if you, assuming this is all oxygen, we say monoxide, dioxide, trioxide, tetroxide, pentoxide, hexoxide. Again, you don't say hexaoxide, you don't say heptaoxide. You say hexoxide, heptoxide, octoxide, and so on. Non-oxide, decoxide. Oxygen's the only one you do this with, which is actually a little strange, because for example, if iodine is the second one, I think it sounds really strange to say triiodide, but that is what you say. So if you have like Pi3, it's phosphorus triiodide. If you have Ci4, it's going to be carbon tetraiodide. It sounds a little strange, but you only change it with O. Okay, and last question, two questions for our examples. Do I have to crisscross these so their ionic charges cancel out? No. These are not ionic. Do not be thrown off by charges. I've seen a lot of people in the past when I'll tell them like nitrogen trichloride or something like that, and they'll think, well, nitrogen is like 3 minus, chloride is minus. Is it 3 to 1? Don't think about ions at all. These have nothing to do with ions. These are not ionically bonded. Ignore the whole thing about their charges. When you name them, when you write the formulas, you just put the numbers down that you need, the number of them you need. So don't worry about ionic charges. Last question. Do I simplify these down to their simplest form? Remember back in our ionic videos, if you had something like Mg2O2, which is not a correct way of writing it, if you ended up with this by crisscrossing, you would have to simplify that down to MgO. Like for example, another example, let's say we have titanium with a 4+ charge and oxygen with a 2- charge, and we want to write the compound here, the formula. Well, if you crisscross it, you could say Ti2O4, but that's wrong. You have to simplify it down. Ionic compounds always get simplified down to their simplest form. But do I simplify these down to their simplest form? No. Big red letters, no. Covalent molecules do not get simplified down even if the numbers are divisible. For example, if I tell you difluorine, which again, this does not actually apply to real life, difluorine tetroxide. Well, what's difluorine? That's going to be F2. What's tetroxide? O4. You might think I would have to simplify this down to be FO2. You do not. If it were ionic, you would have to, but that's covalent, so this is exactly how you have to leave it. Because for all we know, FO2 could be a separate molecule which could have all separate properties. So, if I say difluorine tetroxide, this is exactly what you write. All right, on to our examples. Name the following. So all you need to have is your list of Greek prefixes memorized, and these go fairly quickly. No crisscrossing required, no Roman numerals required. All you do is look at the number of them and say the answer. Dinitrogen trichloride. Why don't you try pausing this and working through the rest. Silicon tetrabromide. Notice you don't say monosilicon. Let me write these down just so you have it written there. So this one's going to be dinitrogen trichloride. This one, silicon tetrabromide. CH4, now that has a common name you should know, that's methane. That's the everyday name, but according to the official rules of naming, we can call this by its true name, its IUPAC name, which is that group in France I always talk about, International Union of Pure and Applied Chemistry. This is going to be 1 carbon, 4 hydrogens, gives you carbon tetrahydride. Please don't mix up hydride and hydroxide. Hydroxide is a polyatomic ion, OH minus. SeO. There's 1 selenium and 1 oxygen. Which one gets the mono? The second one. So this becomes selenium monoxide. You don't say monooxide, you say monoxide. OF2, 1 oxygen, 2 fluorines gives us oxygen difluoride. Please spell that correctly, Fluoride. And finally, P3S, there are 3 phosphoruses, there is 1 sulfur. This is going to be triphosphorus. For us, I'm spelling because I'm trying to get the board right. PHOS, PHORUS. Sorry about that. And the S is going to be monosulfide. Triphosphorus monosulfide. Let's do these the other way, writing out our formulas. All right, so again, this is very simple. It's even easier this way. You just kind of work through it. Dinitrogen trioxide, N2O3. Literally as simple as that. Don't think about charges. Don't think about crisscrossing. You just write it as it is. Silicon tetrachloride, Cl4. Tetracarbon, that's 4 carbons. Decahydride, H10. This has another common name that is butane, which is in like lighter fluid. Sulfur monophosphide, so 1 sulfur, 1 phosphorus, which is phosphide, just like that. Right, SP, yeah. Nitrogen tetroxide, 1 nitrogen, 4 oxygens, easy. Pentanitrogen nonabromide. So that's going to be, penta is 5, so N5. Nonabromide is Br9. N5Br9. Again, disclaimer, almost none of these actually exist, well, some of them. So that's why I'm sometimes like questioning it because I've never seen these types of things. That's because I kind of made up gibberish names here just for the purpose of working through this. Germanium, that is one of our metalloids. Germanium monofluoride would be GeF. And xenon hexafluoride. Xenon, noble gas. Xenon actually does bond under rare conditions. There are exceptions to every rule in chemistry, and even though most of the noble gases don't bond, some of the heavier noble gases can actually bond. Here's an example. Xenon hexafluoride. Well, the rule's the same. There's 1 xenon and 6 fluorines, so XeF6. That's it. This is pretty straightforward. Good luck naming your covalent molecules.